morning, everybody who's here.
Good morning.
Right, close that. And then, oh, no. All right, let's jump back into uh, substitution and elimination. Get some light in here. Feel like a vampire. Share my screen, and we're gonna jump right back in. Hopefully, you have the handout. Um, There we go. I'm gonna do right now. And while we are, while I'm getting this set up, does anybody have any questions about the substitution stuff that we talked about the other day? All right. So we left off yesterday with, yes, recording. Left off yesterday with Sn1. We talked about solvent. We talked about the substrate, preferably tertiary. There's some other substrates that you can do with SN1 reactions on. I'm gonna talk about those in a problem that we're gonna look at in a second. Um, but so today we're gonna look at the E2 mechanism, and I'm gonna take, I'm gonna ask you to do this one on your own. So you'll do that one, and I'm gonna do the bottom example. All right. All right. So in the bottom example, when we do elimination, somebody tell me what the outcome is under normal circumstances. If you do an elimination, remember we only studied four types of reactions, right? Substitution, elimination, addition, and rearrangement. So what's the outcome of any elimination?
A pi bond.
Formation of a pi bond, right? So for this E2 elimination, there's a couple of things to know about it. Again, this is redundant from part one. If you took my class, took me for part one, but you have to have a base. That's one thing that's important. You got to have a strong base in order for elimination, E2 elimination to happen. Uh, this also favors tertiary carbons, right? Because if you eliminate from a tertiary carbon, you're going to form a highly substituted alkene, or your pi bond is going to be substituted, right? So in this case, what we look for are a couple of things, right? We already have a strategy. We need to find our leaving group, which is always going to be the most electronegative atom or functional group that's present, right? It'll never be hydrogen. It'll never be carbon. It's always going to be, if you have a choice, it's always going to be your most electronegative atom. That's how you locate it. So we need to find our leaving group. Here's our base, KOH, which is really, it's not the potassium part that's participating. It's K plus, and then OH. It's a salt, right? Minus. So it's the OH part that's going to be basic. Uh-oh, that looks sloppy. Hold up. I'll just leave it how it is. Minus, plus. Right? So it's the OH part that's going to be doing the proton transfer, not the potassium. All right. So you got your base. You're going to do this in an aprotic solvent. Got to be aprotic. Why? What do bases love? Bronsted bases love. What are they looking for? If you have a Bronsted base like KOH and you put a proton source near it, that's what it's going to react with. So it has to be an aprotic solvent. All right, so you got your solvent, aprotic, you have your strong base. This is a way to identify whether it's an elimination or not. And I have another video I'm going to send today for y'all to look over to reinforce this. All right, I can't remember if I sent one of those elimination videos Monday or not. I'll have to go back and look. But anyway, so you have base, you got aprotic solvent, you found your leaving group, and you're always going to eliminate by removing the hydrogens adjacent to your leaving group on the carbon adjacent. So you got a proton, 2 protons there. You got 1 proton here. How many products am I going to get if both sides are equally susceptible to being removed, both protons?
Is it 2?
You should get 2 products, right? Because the base is going to attack either side. So I'm going to cut this out and put it on another page so we don't have to try to squeeze it all in. And that way we can show it properly. Copy that. And then let me add a page real quick. I should put it. No, let me not do that. Put it right there. Come on. All right. Right, so the base, let me crop this right quick, actually. Crop that stuff off the top. Come on, man. All right. So the base is going to actually come in and again do proton transfer, right? So let's show that. So here's the OH group here. If you're wondering what's going to happen to the potassium, it's going to end up with your leaving group. So the E2 is another reaction that's concerted. And I gave you the rate law for it already. It's the substrate concentration times the base concentration times the rate constant, right? So this is an example right here of the E2. So here now my base is coming in. It's going to grab this proton. The electrons from that bond are going to be put here to make a pi bond. So you got a pi bond forming right here. And then at the same time, you're losing your leaving group. And keep in mind, iodine does have 3 lone pairs on it. All right. So all of that's happening at the same time. It's all concerted. All right. So once you do that, you're going to get a product on the other side that looks like this. Let me make sure I'm not leaving any carbons off. I am. Here. Your pi bond is going to be here. And then boom, like that. That's going to be your first product plus Ki. Right? Because the iodine leaves as a negatively charged atom. The potassium is positively charged, so it's just going to form a salt with iodine. All right. And then by the same token, the OH can come in and pull off the proton on the other side. So I can have the OH here. It's negative and it's coming here. Right. And when that happens, this pair of electrons is going to come here. Uh-oh, sorry. Right there. Right. And then the leaving group is going to leave the same way. Right. Like so. This is not happening simultaneously. It's either happening on one side or the other, but you're going to get both products. Right. So in that case, the double bond is going to be on the end. So let's see what that looks like. So this is here. Right. That's the product plus Ki. Right. Any questions about that? So the rate again is K times the concentration of the substrate times the concentration of the base. So if you do anything to the base or the substrate, concentration wise, if you double one or triple one or double them both, then it's going to have an effect on the rate. Right? What do you think happens if I double them both? What happens to the rate?
It quadruples.
It quadruples. Right? The rate should increase by 4. If I double one and half one, what's going to happen to the rate?
It'll go up by 1.
Right? It will. So it'll be no change, right?
Right.
Yeah. Yeah. So no change. If I double one and half one, it's still 1x, right? So there's no change in the rate. But that's the point is that the rate is dependent on both. So the 2 is in the E2 is bimolecular. Let me put that up here too. That we were looking at E2. Come on, man. right? That two-term rate law means that this is a bimolecular mechanism. Right? Bimolecular is dependent on both. So if we go back up here to the to this other, do I have that? I don't have that. No, that's just substitution. Never mind. I'll show you. I'll draw it in. So that when we talk about that the transition state, let me show you that for the E2, and then talk about one other important feature, right? So if this is my if this is my substrate, when the base is coming in, sue Amazon. When this is coming in here, right, you got a partially formed bond between the H and the O. And I forgot to put that up here too, because you get Ki, but you also get water as a side product. All right. So the base is coming in, breaking that carbon hydrogen bond. And then by the same token, this bond is partially broken. And then your pi bond is partially formed. And then your bond to your leaving group is also partially broken. So that's what the transition state would look look like, excuse me, for an E2 reaction, or reaction that goes through an E2 mechanism. Right? And then that's why it's bimolecular, right? Because the base as well as the substrate are participating. So that's why it's a two-term rate law. The rate determining step is right here. The removal of the proton and loss of leaving group happens since it's concerted. This is your rate determining step. So this is what the transition state looks like. And this love is really irking me. Sorry about that. All right, so that's what the transition state for the E2 looks like. Partially broken bond between C and H, partially formed pi bond, partially broken Ci bond, and then a partially formed HO bond. All of that's happening all at once. It's all concerted. Any questions about that? So this is forming. And then this is breaking. And then that pi bond is forming. And then the Ci bond is breaking. All that's happening in the transition state. All right, so we go back up to here. There's something we can say about the products as well, right? In the notes under E2, it talked about Zatev's rule, right? So this would be my major product. And then the other product would be my minor product. All right. So this follows Zatev's rule, which tells me that the more substituted alkene is going to be the major product, right? So you can look at the two double bonds and see, somebody help me out. What's the substitution pattern for this double bond right here? Is it mono substituted? Is it di substituted? Is it tetra? Is it tri?
Die substitute.
It's di substituted. Good. And then the alkene on the other side here is tri substituted. So it's more substituted. So that means that's what Zatev's rule predicts, that the elimination is going to result in the more substituted and by the same token more stable alkene. So I'm gonna put that down here. So follow Zatev's rule. So a more substituted alkene is going to be your major product. All right. Questions? Any questions about that? Questions about the substitution pattern? Questions about anything? You'll see.
I have a question.
Go ahead.
If this was in a protic solvent, would it take longer, or could the reaction not even occur?
If it was in a protic solvent, you mean?
Yes.
Yeah. It probably, you probably have like very little elimination happening, because a protic solvent is just gonna do acid-base chemistry with the base, and that a protic solvent with a low pKa, that proton is gonna fly off to that OH group. So
Okay.
that it won't even have a chance to, because the pKa of these protons is a little higher, right? This is probably gonna be somewhere in like the 20s, high teens, 20s. Whereas if you do it in something like acetic acid with a pKa of 4.7, there's no competition. The base is just going after the acid. Yeah.
Okay. Thank you.
Great question. All right. So we talked about Zatev's rule. We talked about, and I forgot to mention this too. So these protons that are next door to where your leaving group is, we call those alpha protons. So that's how you identify. Let's call it alpha. Ooh, that's bad. Hold up. Let me fix that little alpha up. So it's called an alpha proton. That just means that it's adjacent to your leaving group. All right. Let me put that arrow back too. Sorry about that. Any other questions?
How do you know it's di substituted and tri substituted?
I'm gonna throw my coffee through the screen. Well, no, I'm not, because then I have to buy a new computer. So if you look at the double bond itself, you're just looking at the number of carbons attached to it. Right, so you got 3 carbons attached here. 1, 2, 3 attached to the alkene itself. On the other one, you got 2 carbons. A carbon here and a carbon here. Right, so the mono would be 1 carbon, di is 2, tri is 3, tetra is 4.
Okay, thank you.
All right, you're welcome. All right, so the E2 is going to follow a similar pathway to the Sn2. It's going to have loss of leaving group is your rate determining step, and that's facilitated by the base removing the proton adjacent on the carbon adjacent to where that is. It's going to be a two-term rate law. It's going to be concerted. All of those things that E2 and Sn2 have in common. So we go back up to here, and you have to do it in an aprotic solvent for obvious reasons, because you need a strong base. So if you do it in a protic solvent, then the base is not going to do elimination. It's just going to continually do as proton transfer with your base, with your solvent. Sorry. All right. So let me put the products in here.
I have another question.
Yeah, go ahead.
If the DCM, if it happened, like if you were in the lab and you didn't clean out your test tube correctly and it had like a little bit of acid, could that totally like mess up the reaction and contaminate it, or would it just?
Not totally, but it would it would probably diminish your percent yield though.
Okay.
Yeah, it would. If it's just like a trace amount of acid, then it's not gonna kill a reaction. But if you there's a difference in something being a solvent, which means that it's dissolving up all of your reagents as and being used as a medium, versus a trace amount of that's not gonna kill it. It'll probably take a little bit away from the yield, maybe, depending on how much.
Okay, thank you.
Yeah, good question. That's plus that. And I'm gonna put down here plus 2 Ki plus 2 waters. Right, and this is major. All right. All right. So now we're gonna look at the E1, and then we're gonna look at an example of each one of these in the problems below. And then on Friday, we're just gonna have a work day. We're gonna work through some problems that are in this packet. We're not gonna do this page here. We're not gonna do that. We're not gonna do all of it anyway. We'll probably just do the problems 2, 3, 4, and 5. But we can work through those. Actually, we can work through those today. Let's just do the E1 real quick, and then we'll come back to that. All right. So the E1 is similar to the Sn1. It's unimolecular, which means that the rate law is only based on the substrate. All right, so it's just K times the concentration of the substrate. There's no base necessary for E1. Right, so you see right away this is being done in the presence of sulfuric acid. So there's no base, right? The elimination happens after you form your intermediate. So the first step is exactly like the Sn1. It's the loss of leaving group, right? In this case, that's going to be a little bit different because OH is a bad leaving group. So we got to do something to it. What's one way we can turn OH into a better leaving group? Now, this was in not the last section, but the section before. What's an easy way to turn it into a better leaving group?
You can make it into water.
Yeah, turn it into water, right? Protonate it, give it an H plus, and turn it into water, and then it becomes a great leaving group. And so this is a classic E1 elimination right here. It's just a acid catalyzed dehydrations, right? So it's loss of water, and this is a classic example. So let's look at what happens. So we got sulfuric acid, which looks like this. Come on, glove. I probably should have made my own anti-palm glove for this iPad because this thing is suspect. It must have a hole in it somewhere. All right, so that's that. And so the first step in this particular case is just going to be proton transfer from the acid, right, to the OH group. It's important to understand too, like here, since there's no base, you got to have some way to do the elimination. Let me put some long pairs in here too. Right? So what's the outcome of this part right here? Right? We know we're going to get this. I'm gonna put this in brackets because this is an intermediate. We're going to get this. And that's positive. Right? And then what's the conjugate base look like from sulfuric acid? What is that going to look like?
SO4 minus.
Good. Well, HSO4 minus because you still have one H left. So I'm
My
gonna.
bad.
Yeah, no, you good. You good. Thank you. You in the house. Right? So that's my conjugate base. Right? And the reason I'm saying this is because in order to eliminate, you still have to remove an alpha proton. Right? So the elimination is either going to happen from the conjugate base, or I'm just going to show this, and this is an equilibrium with this carbocation intermediate, like that, right? But the alpha protons are still here, right? Right, those are my alpha protons. In this case, it doesn't matter, right? Which ones we remove, it doesn't matter because it's symmetrical. Let me fix that. Sorry about that. Right, and then so in this case, we can take an alpha proton off of either side and we'll still be good. But the question is, so we're going to lose water. So now the question is, which species is going to do the proton transfer, right? Is it going to be water or is it going to be the conjugate base? The truth is, it can be both. It can be either or. So I'm going. Which one do you want to use? Which one do you think is the easiest to see?
The conjugate base.
Conjugate base. All right, let's use that. So the conjugate base, I'm just going to draw it here. All right, that's negative. And then, come on, pen. Son of a biscuit. I'm suing Amazon. This glove sucks. So it's here, like that, right? So that's just going to come in, donate a pair of electrons here, and then boom, that's how your double bond gets formed. So you end up with this as your product. That plus sulfuric acid, because it got regenerated right there when you brought in the conjugate base to do the deprotonation. or the proton transfer plus water. It's frozen. It'll go where it's supposed to go in a second. All right. So that's my alkene plus sulfuric acid plus water. And the sulfuric acid is always going to get regenerated. Even if you use the water as your base to do proton transfer, you will get H3O plus, and then that'll do proton transfer with that conjugate base of sulfuric acid. So either way, you're going to get sulfuric acid back from this reaction. And then just like the Sn1, the leaving group loss is the rate determining step. So this step right here is rate determining, right? The loss of leaving group. It's not the proton transfer at the beginning, and it's not the elimination part. It's the leaving group leaving, which is the rate determining step. All right, and I have a list down here of leaving groups. You can look over that and make sure you know like how to determine the leaving group ability based on the pKa of the conjugate acid. So I'm gonna write that in down here. So the loss of leaving group, that's my rate determining step. All right. Any questions about the E1? Anybody still writing or screenshotting? Let me know before we move on. No questions. All right. Let's go down to, if you have the handout, let me scoot down here. First, let me put a date on here so you'll know what you're looking at when I upload this. Today is not the 16th, it's the 17th. And this is also the 17th. All right, let's look. And then, so if you look at the handout, this is, you have a list of aprotic and protic solvents here, right? And you'll see the either the name of the solvent or the acronym for it in a specific problem. And then your protic solvents, acids, alcohols, water, and then non-carboxylic acids like sulfuric acid, phosphoric acid, so on and so forth. And then on this list, you can see the leaving group ability, right? Iodine is your best leaving group because the conjugate acid pKa is -10. And so what this pKa is measuring now is not iodine, but it's measuring HI, which would be the conjugate acid. So whatever the leaving group is, if you put a proton on it, then that's the conjugate acid, right? And that's what you're measuring with that pKa. So the lower the pKa, the more stable the leaving group is, and the faster it leaves. Right. This is just like what we learned in part one when we did acids and bases and we did hires, right? Hybridization, induction, resonance, electronegativity, size. Those 5 factors that stabilize conjugate bases. That's the leaving group is identical to a conjugate base, right? So you would use the same concept or the same idea about thinking about how stable or unstable a leaving group would be. All right. So let's go down and do some examples real quick in the time we have left. Right, we're going to skip this top example because we got a bunch of other examples to look at. All right, so let's look at this reaction right here, right? And the question is asking what mechanistic pathway would you follow to get what the following reactions follow? Would you expect them to follow, right? So it's either substitution or elimination. And let's look at all of our circumstances, right? We got all of our conditions. We got acetone, which is protic or aprotic.
Aprotic.
Aprotic, good, right? And then we have, if you look in the product, you got inversion of stereochemistry. Right? You can see here that that's on a dash, and we started out with the leaving group. Uh-oh, sorry, wrong pen. On the wedge, right? That's a dead giveaway right there. And you can see that this is my nucleophile. Oh, snap. Thought there was a highlighter. You can see that this is my nucleophile, and that sulfur nucleophile swaps out with the leaving group. You can see that in the product. So what type of reaction do you think this is, and what mechanism do you think it follows?
It's
Is it a-
substitution in Sn2.
It's a Sn2 substitution. That's exactly right. Right. And all the conditions give it away. You have the inversion of stereochemistry, you got aprotic solvent, you have a secondary substrate, and then you have a good nucleophile. All right, so it's Sn2. So which one of these would be the rate law? It's the two
D.
means it's bimolecular, means it's a 2-term rate law.
D as in dog.
D as in dog.
Yeah.
I agree with that, right? Acetone is the solvent. It doesn't participate in the rate, so it can't be B, and it can't be A or C because those are both 1 term. So it has to be a 2-term rate law. So we're going with D. All right, and then number 4 asks this question. Shucks. Let me go back and ask a question that's not on here, but that you should be able to answer. Which one do you think is going to happen faster?
Would it be the first one since it has a lesser pK?
You said the first one has a lower pK.
Yeah.
I think, yeah, I agree with that. This one. Because the leaving group is better. Right, if you compare the pKa's, you're exactly right. It's got a minus 0.6 pKa, and then the acetate leaving group has 4.76 pKa. Right, so the lower the pKa, the better the leaving group. So the tosylate is a much better leaving group. Right, so yes, the top reaction will be faster. Good. All right, let's go to the next question. It says if the concentration of sodium methyl is decreased by 10 times, what's going to happen to the rate? If I change one of those terms and I cut it by 10, what's going to happen to the rate?
Would it be, it would decrease as well?
It should, by the same amount, right?
Right.
So it should be a 10 times rate decrease. All right. Questions about that? Anybody? All right. By the same token, if I increased it by 10, it should be a 10 times rate increase. If I increased it by 20, a 20 times rate increase. All right. Let's look at the last question on this part of the handout. All right. This is a reaction R2 methyl 3 bromobutyl benzene with sodium methoxide gives two products. That's very important. That's a clue. That gives you two products. Choose the best representation of the transition state. So that's what we're thinking about. But before we can know what the transition state looks like, what do we need to know?
What type of mechanism?
The mechanism. Got to be Sn1, Sn2, E1, or E2. Based on the products, you can see that it's a substitution. Am I right?
Yes.
Because you have bromine here, and then on the other side, that gets swapped out with the ethoxide group from sodium ethoxide. And the fact that it's in a protic solvent, ethanol, and you get two products in equal amounts, two enantiomers in equal amounts. Which type of substitution is it? Right, you get a racemic mixture for your products.
So it'll be SN1.
It's SN1. Good. So now which transition state matches for the SN1? Which ones can you rule out right away? Remember, if it's SN1, the nucleophile is not involved in the rate determining step, which is the loss of leaving group. So could it be transition state 1? Which actually has the nucleophile involved?
No,
Can't be that. Could it be 2?
no.
No. Both of those are bimolecular, right? You got the nucleophile and the leaving group both involved, and the nucleophile and substrate both involved. And we just said it was SN1, right? And we also said that the SN1 was unimolecular. That means that in the rate determining step, only the substrate is involved, right? So between 3 and 4, which one do you think?
I think 3.
3?
That's just what I think.
Same.
Can you tell me why?
Because just to me, it don't make sense for bromine to have a partially positive charge.
Right. That's exactly right. Bromine in transit in TS4, the bromine should not be partially positive. It's got 3 long pairs around it, plus it's taking a long pair in that bond that's breaking, right? So it should end up negative. So it shouldn't have a partial positive charge. So it's 3. The carbon, where the leaving group is, because that. Hold on. Hold on. Thank you, everybody who was logged in. Thank you for your patience too. I really appreciate that. Sorry about that. I was processing another video from yesterday. Yeah, so 3 is your transition state because the carbon where the bond is breaking is becoming positive and the bromine is becoming negative. All right, that's really important. All right, we're gonna stop right here. Instead of doing another example and going overtime, we'll stop here. We're gonna pick this up on Friday, and hopefully everybody has this handout so you can follow along while we're working, because there's no way you can write all this stuff down and then follow and pay attention at the same time. So hopefully you got the handout. It's on Blackboard in the assignments folder. And yeah, we'll pick up on Friday. Any other questions?
Dr. Russell, can you scroll up to the top of the document?
This part?
No, to the very top.
All the way to the top.
Yeah. Which one were we supposed to do on our own?
the second E2 over the first E2 reaction.
Okay, thanks.
Mhm. All right, any other questions? All right, I'm gonna stop sharing and stop recording. My mouse not working.